In this video lecture, we'll be solving this problem, cheapest flights within K stops. So we're given n cities connected by some number of flights. So we have solved this problem using BFS approach in the previous video. I'll attach the link to that video in the description below, so make sure to check it out. So in this problem, we're given n cities which are connected by some number of flights. So you're given an array flights where each element in that array is a tuple of integers representing a starting city, an ending city, and the price to move from the starting city to the ending city. Also, we're given three integers, source, destination, and an integer k representing the source city, the destination city, and the maximum number of stops which are allowed to move from the source to destination city. If there is no such route, then return -1. So in the input will be given a flights array having n tuples, a source city, a destination city, and an integer k representing the maximum number of stops from source city to destination city. While in the output we have to return an integer representing the cheapest price to move from source city to the destination city, such that there are at max k stops along the route. Fine. So let's better understand the problem statement using an example. So here we have an example of a network. We have 4 cities numbered from 0 to 3. And this is a directed graph. 0 is our source city and 3 is our ending city. So the source city is 0 while the destination city is 3, and the stops that we are allowed are 1. So we are allowed to have at max 1 stop to move from the source to the destination. So let's see the possible routes from the source city to destination city. So one of the paths would be to move from city 0 to city 1, then from city 1 to city 3, fine, giving me a cost of 100 plus 600, which is equal to 700. Then we have another path where we move from city 0 to city 1, then from city 1 to city 2, then from city 2 to city 3, giving me price of 100 plus 100 plus 200, which is 400. But this cannot be a possible route because we have 2 stops while we move from the source city to the destination city, stop 1 and stop 2. Hence the only path that we have is the first path, which has a price of 700 units. Hence the answer for this particular input test case would be 700. Fine. So let's see how we can solve this problem. One of the ways to solve this problem is to use a BFS search with a little modification, and I have solved this problem with BFS in my previous video, which I have attached in the description below, so make sure to check it out. In this video lecture, I will be solving this problem with a Bellman-Ford algorithm. Let's see how to do that. So this is a sample graph which I have taken, which has 5 vertices numbered from 1 to 5, and our source city is city number 1, destination city is city number 3, and k represents the maximum number of stops which are allowed along the path from source city to the destination city. So since I want to find the single source shortest path from the source node to the destination node, I can use Bellman-Ford algorithm, which is a dynamic programming algorithm used to compute the shortest path to all nodes starting from a particular source node. So my Bellman-Ford algorithm will give me the shortest path till node 2, 3, 4, 5 and 1. Fine. And I can return the shortest path up to destination city, which is city number 3. So it works on a dynamic programming idea. So what do we do in this algorithm? So I'm assuming that you have a basic knowledge of Bellman-Ford algorithm, how it works, its implementation, details, etc. So if you do not have idea about Bellman-Ford algorithms, then make sure to learn about it. I will attach the resources in the description below, so make sure to check them out before you proceed in this video. In Bellman-Ford algorithm, let's say we have a graph of n vertices, then the shortest path or the path which has the least cost may have n minus 1 edges at max. Fine. So what I can do is I simply start from 1 edge till n minus 1 edges, and I iterate from 1 to n minus 1, and each time I perform my relaxation over the edges. So first time I find the shortest path with 1 edge. So in the very first iteration I calculate the shortest path which has at max 1 edge along in the path. Then in the next iteration I find the shortest distances which has at max 2 edges in the path. Then I find the shortest distances which has at max 3 edges in the path, and so on till n minus 1 edges. Fine. After I end this process, I have my distance array prepared where I have the shortest distance till each node of the graph. Fine. So this is how the Bellman-Ford algorithm works. But here what we have to do in this particular case, we know that, so for this particular case, we know that to reach the destination city, we must not have nodes more than k plus 2, because at max we may have k intermediate nodes and 2 counts for the source node and for the destination node. So while giving me a total k plus 2 nodes, so we may have at max k plus 2 nodes in the simple path from the source to destination. So there is no need to process n minus 1 edges. So all I can do, so instead of iterating from 1 to n minus 1, I iterate from 1 to k plus 1. Why k plus 1? Because we know that for a path having k plus 2 nodes, I may have k plus 1 edges at max. So this is the longest path which we may have while computing the shortest path from source to destination. So we may have k plus 1 edges. We can't have edges more than k plus 1. Fine. How will this algorithm work? So let's dry run the approach which I explained here. Okay, so I iterate from 1 to k plus 1 and I copy my distance array into this temp array. So at the very first iteration, I want to find the shortest path which has exactly 1 edge starting from the source city. So I iterate over such edges. So first I iterate over this edge that is connecting the city 1 and 2. So I can see that the cost to move to city number 2 would be 0 plus 10, that is 10. So I can see that the cost for this city, which is the source city, is already evaluated in the distance array. It is 0. So I can perform this relaxation. That would give me 0 plus 10, that is 10. So I update my temp array to 10 because I can see that the distance that we already have till node number 2 in this temp array is infinity, and this 10 is better than the infinity. Then I check this edge and I see if the node 1 is already relaxed. If the distance to the source node has already been computed, I can see that the distance to till this city 1 is already computed. It is 0, so I can perform this relaxation. That would give me 0 plus 50 as 50. So I can update my temp array here. So I check if the distance for the city number 3 is better, which we have calculated here, than the one which we already have in this temp array. And the answer is yes, 50 is better than infinity. So I update my result here. Then I move to the next edge, which is this edge 2 to 4, and I check if the distance till 2 is already computed or not. But I see that the distance till node number 2 is not computed in this distance array. Hence, I cannot perform the relaxation for edge 2, 4. Same goes for these edges 2, 3, 4, 3, because I do not have a valid distance for node number. So I cannot perform the relaxation for this edge and this. I also do not have a valid distance for node number 4 in this distance array. We have infinity, so we haven't evaluated the distance from the source city till node number 4. So I cannot perform the relaxation for this edge 4, 3 and 4, 5. Same goes for node number 5. I can't perform the relaxation for this edge as well. Fine. Hence, this is my final temp array. And I have performed the relaxations for all the paths which has at max 1 edge. So I have calculated the shortest path till city 2 and city 3 from the source city, and that distances are stored in this temp array. And after I have processed this temp array, I will copy this temp array into my distance array. So finally the configuration would be, then I move to the next iteration, which is the iteration number 2. And I again copy my distance array into this temporary array. Now the temporary array will store this distance array 0, 10, t, infinity. So in this iteration, I will find the shortest path which has at max 2 edges. Fine. So let's do that. So I can see that let's perform the relaxation for this edge, which is 2, 4. I ask, can I perform this relaxation? And the answer is yes, because the distance till node number 2 is already computed. We have the distance as 10. So 10 plus 10 would be 20. 20 would be the distance, the shortest distance from the source city 1 till the city number 4, while we have at max 2 stops along the way. Here. Fine. So I ask, whether 20 is better than the distance which you already have in this temp array, and the answer is yes, 20 is better than infinity. So I replace infinity with 20. Then I check this edge which is 4 to 5, and here what I'm checking that, then I check this edge which is from 4 to 3, and I ask if I can perform the relaxation along this edge, and the answer is no, because the distance till 4 is not evaluated in this distance array. We have distances till city 2 and city 3 only, so I can extend exactly one edge from these cities. I have extended an edge 2 to 4, and I have performed the relaxation here for node number 4. I can extend this edge as well. So let's perform the relaxation for edge from 2 to 3 if it is possible. The price to arrive at city number 3 through node number 2 would be 10 plus 30, which is 40. I ask if 40 is better than the price which you already have, and the answer is yes. The price which you already have is 50, which is along this path, but along this path, that is from 1 to 2 and 2 to 3, I get 40 units of price. So I replace 50 with 40. Fine. So then I move to next iteration. So from node number 3, I cannot perform the relaxation for any other edge because there is no outgoing edge from city 3. So I simply iterate over all the edges, and it is not possible to perform the relaxation for edges other than the edges which I have already. So I move to the next iteration. So I have my temp prepared here, and then I copy my temporary array into the distance array. Fine. After the second iteration. So at this point, I have found the shortest paths from the source city to those nodes which are at a distance of at max 2 edges. Fine. Let's see the final configuration of this distance array. Then I move to the third iteration, and in the third iteration, this is the last iteration because k plus 1 would be 3. So in the last iteration, I will find the shortest path which has length of exactly 3 edges starting from this source node, and I copy my distance array into this temp array. So here I can see that I can perform the relaxation for node number 4. So now I can perform the relaxation for this node number 4 because I have the distance till this node. So I have the distance from city number 1 till city number 4. So I first try to relax this edge which is from 4 to 5, and I ask if I can do so. The distance till 4 is 20, and 20 plus 5 would be 25, which is the distance till node number 5. Is 25 better than the distance which you already have? And the answer is yes. So I replace this infinity with 25. Then I check if I can perform the relaxation over this edge 4 to 3. So till 4 I have the distance as 20. Can I perform this relaxation? So 20 plus 15 would give me 35. Is 35 better than the distance which we already have for node number 3? The answer is yes. So I can perform this relaxation. I replace this 40 with 35. So that's all. I can perform the relaxations for node number 4, and I have evaluated the distances till those nodes which has at max 3 edges. So I have found the distance. So I have checked the distance. I have found the shortest distance till node number 3 through this path which has 1 edge, that is 1 3, through the path which has 2 edges, which is 1 2 and 2 3, through the path which has 3 edges, which is 1 2 2 4 and 4 3. That's all I'm allowed to do. I'm not allowed to find the shortest path till node number 3 which has 4 edges, because we have a path till node number 3 which is even better than all the paths which we already have. That is the path from 1 to 2, from 2 to 4, 4 to 5 and 5 to 3. This will cost me 10 plus 10 plus 5 plus 5, which is 30 units of price, which is better than 35. But we are not allowed to do so because it has 4 edges, and we are only allowed to relax till 3 edges. So my job is finished. I have calculated the distances till all the nodes with at max 3 edges. Fine. So 3 edges means we have at max 2 intermediate cities which I can explore. Fine. So I break this loop right here, and I copy this temp array into the distance array. So the final distance array would be, so this is my final distance array. It has distances from the source city till each node. Fine. So this is how I solve this problem using Bellman-Ford algorithm. Fine. And this is my final distance array. Let's see the implementation of this approach which I explained here. in the next slide. So this is my find cheapest price function, which takes in the number of flights, the flights array itself, the source city, the destination city, and the maximum number of intermediate stops allowed. So I initialize my distance array, which will store the distance of all the nodes from the source node. I initialize with infinity with a very large number. So infinity can be int max, which is the upper numeric limit. Then I initialize my source node with 0, and I iterate from 0 to k, that is exactly k plus 1 times, because I want to relax till k plus 1 edges, because the maximum number of stops puts an upper bound here. I copy my distance array into the temporary array. So here I am declaring a temporary array where I copy my distance array. Then I perform the relaxation over the edges. So here I check if there is a node which is already, if there is a node up to which we have the distance calculated, in that case I can relax the edges which are outgoing from this node. So I relax them here if it is possible. I find min of the distance which we already have with the distance which we calculate from this node, which is flight 0. Fine. So here I am performing the relaxation. So this is the relaxation equation. Then I'm again copying my temporary array because it has been processed here. So I'm iterating over all the edges here. Then I copy my temporary array into the distance array, and finally I check if the distance till the destination node is a very large number, means I haven't reached that node. If that is the case, then I return -1. Otherwise I return the distance till that node, which we have calculated in this distance array. Fine. So this is how I solve this problem. Let's see the implementation of the idea. Let's see the code implementation of this idea. So we're iterating over all the edges k plus 1 times, which will take e multiplied by k time complexity. Also in each iteration, I'm swapping the temporary array with the distance array, which will take k into n time complexity. Final complexity would be k will be in common e plus. So I hope you got how I perform the analysis here. I am iterating over k plus 1 edges in the outer loop here. So this is the outer loop. I'm iterating for k plus 1 times over all the k plus 1 edges. Then that will give me e, which represents the number of edges, multiplied by k time complexity, while in each iteration, in each of the k iterations, I'm swapping my temporary array with the distance array, giving me a linear time complexity, which will give me a final time complexity of k multiplied by e plus n, while the space complexity for the given implementation is big of n, because I'm using a distance. Fine. So let's see the code implementation for this approach. So this is my solution class, where we have my find cheapest price function, which takes in the number of flights and source city, destination city, and the maximum number of intermediate stops. I declare my adjacency list for storing the graph. Then I prepare the adjacency list from the given set of flights. Then I declare a distance array and initialize it with a very large value. Then I initialize my distance array with 0 for the source node. Then I iterate for k plus 1 times. I copy my distance array into the temp array for each iteration, and then I iterate over all the flights or edges, and I perform the relaxation where there is a scope of relaxation, and finally I store my temporary array into the distance array. At the end, I check if we have calculated the distance till the destination city. If it is the case, then I return that distance, otherwise I return -1. Fine. So this is a very simple implementation. It was just Bellman-Ford algorithm with a little modification. All we did is to just iterate for k plus 1 time rather than iterating for n-1 times. This is the implementation in C++ language. Let's see the implementation in other languages. So this is the implementation in Java language, and this is the implementation in Python language. So that's all for this video. If you like the video, then hit the like button and make sure to subscribe to my YouTube channel and give your feedback in the comments below. I will see you in the next video. Till then, take care. Bye bye.